So this is the topic of our lecture number 6. Hello, everybody. Let's get started. Are you ready?
Yes.
And you? Okay. So today we will consider differential equations, linear differential equations, homogeneous differential equations with constant coefficients. So I mean, so last time we have discussed the equations of the form x prime equals a of t times x, where x is a vector, x is in Rn, a is an n by n matrix. Hello, Kathy. So a is an n by n matrix. This was last time, and today we will consider linear equations of the form. So x prime, I will omit the bar above the vector. X prime equals a times x. So a is a constant matrix. The entries of this matrix do not depend on t. And this is a homogeneous linear differential equation in Rn. So x, by x I mean n vector. Today we will discuss this particular case of linear equations. This is a comma. And first of all, I'd like to show, to discuss the fact that the solutions of this differential equation are related to the eigenvalues and eigenvalues and eigenvectors of the matrix A. So do you remember the notion of an eigenvalue and eigenvector? Or shall I recall this? So eigenvalue, so V is an eigenvector of an n by n matrix. It should be a square matrix. If V is not 0, it must be non-zero, and AV equals what? Some constant lambda times V. And if this is the case, lambda is called an eigenvalue. So lambda is an eigenvalue of the matrix A, associated with this given eigenvector. Okay, so we will use this definition. Okay, and the first lemma to be proved today, lemma number 1. So if V is an eigenvector of A with an associated eigenvalue lambda, with an associated eigenvalue then the function x of t, which is equal to e raised to the power lambda t times v, is a solution to this differential equation. Let's prove this. Okay, let's take the derivative x prime of t. Let's consider this function and take the derivative. So v is a constant vector, so we must differentiate this coefficient. It is multiplied by the function depending on t, And the derivative will be equal to lambda times e to the power lambda t times v. So the vector v is multiplied by this constant, and we can switch the places, the positions of these two coefficients. We can switch them, e to the power lambda t times lambda times v. Then, by definition of an eigenvector, we can see that lambda v is equal to av. Well, so we can replace lambda v by av will be equal to e to the power lambda t times av. Okay, now we can see that the constant, so this is so if we fix t, then this is a constant, and it is multiplied by the matrix and the vector, and we can switch the matrix multiplication by the matrix and multiplication by a scalar. It is equal to a times e to the lambda t v. And so, but this is exactly x of t, because we have started with this formula. X of t is equal to the product e to the lambda t, the constant multiplied by v. So it is, by the assumption, it is x of t. So we can see that this function satisfies the differential equation equals a times x of t. So this proves that this is a solution of the differential equation. So to find a solution of the differential equation, we can proceed in the following way. We can find the eigenvalues, eigenvectors, and take these functions as solutions. This is another way to solve matrix differential equation. The first way was discussed on the preceding seminar. We tried to reduce this vector equation to a single nth order differential scalar nth order differential equation, right, by introducing so some manipulations, right, and then solve it. But sometimes this method is more efficient. So for different situations, the first method or the second so is preferable. So we can't decide in advance, but sometimes this method is more efficient. It is more easy to find eigenvectors and eigenvalues. Well, and to state the general result, so this I will state the general result in the theorem number 1. So if the matrix A has n linearly independent eigenvectors, v1, v2, vn, with associated eigenvalues lambda 1 lambda n. They are eigenvalues. Then the general solution of the equation x prime equals ax is given by the formula. This is a linear combination of the vectors of having this form, of the vectors of this form. It is the linear combination not let it be ck e to the power lambda k t vk. K runs from 1 to n. So this is the general equation, the general solution of this differential equation. Okay, I'm going to prove this. Okay, so first of all, I'd like to show that any function of this form is a solution. The linear combination of ck multiplied times e to the power lambda k t vk, k runs from 1 to n, is a solution. So to check this, so it is very easy. We know that we know first that each function e to the power lambda k t vk is a solution by lemma 1. Is it clear? So it follows from lemma 1. Okay, and next we take the linear combination of these functions, each of which is a solution of our differential equation. So next we can apply the linearity principle, right? So by linearity principle proved last seminar, by linearity principle, the linear combination of solutions is a solution of a homogeneous differential equation. Okay. The first part of this theorem is proved. So we have shown that this linear combination is a solution of a homogeneous differential equation. Next, I'd like to show that any solution can be represented in this form. So I want to show that there are no other solutions. There are no solutions which has another form, the form different from this. Right? So any solution, sorry?
So no missing solutions outside this?
No missing solutions, right? Well, so if I consider any solution of this differential equation, it can be represented in this form for some constants. Let x of t be any solution of x prime equals ax. So we are given that the eigenvectors, so the matrix A is an n by n matrix, and so n linearly independent vectors form a basis in Rn, right? So v1 dot vn form these vectors form a basis in Rn, and this means that if we fix t for any fixed value of t, we can represent x of t as a linear combination of these vectors with some coefficients. I don't know, so these coefficients are of some particular form, but it is true that any solution at each fixed time value of t can be represented as a linear combination of these basis vectors with coefficients depending on t, right, times vk. So for each t, we have the set of coefficients. And they vary with t, and so the coefficients are some functions depending on t. I want to show that tk of t is equal to ck, so tk of t, not some arbitrary coefficients, but they have some, they have the form of the product ck times e to the power lambda kt. So they have some predicted form. Well, let's show this. So since x of t is a solution, then this function must satisfy the differential equation, right? So let's find x prime of t. It is equal to the linear combination tk prime of t times vk Okay. On the other hand, x prime of t is equal to a times x, because x of t satisfies the differential equation. What is a times x of t times x of t? It is equal to a multiplied by the sum k runs from 1 to n tk of t times vk. Since a multiplication by the matrix is a linear operator, then we can rewrite this sum as the linear combination of this a applied to this vector okay. So for the fixed value of t, this is a constant, and this constant can be moved through the through this operator, through this operation, right? It is equal to tk of t times a applied to the vector k multiplied by vk. Well, because this is a constant. And since we know that vk is an eigenvector, then we know that ak is equal to lambda k times vk. And I will rewrite it in the form, the sum k equals runs from 1 to n tk of t times lambda k vk. Okay, so we have started with x prime of t. We have represented the derivative of this function in two ways, this way and this one, right? So I will use maybe the colored chalk. Look here, we can see that x prime of t is equal to this linear combination, and at the same time it is equal to this linear combination. But we know that the vectors from v1 to vn form the basis in Rn. So the expansion with respect to the basis, expansion of the vector x prime of t with respect to the basis relative to the basis is unique, because this is a basis. So we must equate the coefficients of vk's. So it follows that this yields that tk prime of t, we should equate tk prime of t and tk of t times lambda k. We have obtained this scalar linear differential equation. If we solve this equation, we will get the solutions. We will obtain tk. So we know how to solve this, because this is a scalar differential equation, and the variables are separated. We can separate variables. So we are trying to solve this. I will use that part of the green board. So I'm trying to solve this. Sorry. T prime k equals lambda k times tk. Let's separate the variables. Dtk over tk equals lambda k dt. We have separated variables, then integrate both parts. Then we get that the logarithm of the absolute value of tk equals lambda kt plus c, from which it follows that tk can be represented as ck times e to the power lambda kt. So this is a common procedure, so I think it should be no problem with this, solving this equation. So we have proved that the coefficient tk have this this form. I think it's clear. So theorem is proved. We're done. The questions?
How groups tk is the coefficient?
So I solved. I have solved this differential equation. So it is very easy to solve this. I have separated the variables, and after this, so I have obtained this. And if we take the exponent raised to the power ln tk, it is equal to e to the power lambda kt plus c. Plus c goes to multiplication by ck, and e to the power ln tk means that tk equals ck e to the power lambda kt. So this is the usual procedure, common procedure. And maybe some questions here, right? Right.
How does proving tk equals to that?
To this.
No, to ck. So we wanted to show that tk.
I want to show this. It is not proved. So I want to show this. But the procedure is, so since this is the basis at each value of time t, for any t fixed, x of t is a linear combination. But if if t varies, then we obtain the function. We get the function x of t with the coefficients depending on t. And I want to show that tk of t is equal to some constant multiplied by e to the power lambda kt. So not arbitrary function, but the function having this form. How to solve this? How to prove this? So it can be derived from the differential equation. So I have shown that we can obtain the differential equation for finding tk. It's this. And after this, I solved this differential equation and have obtained the the form of the function. Okay, should I recall this procedure or not?
I understand all the procedures you did.
But
But my question is, we're trying to show that
this.
We're trying to show that any solution can be
Right.
So how does showing tk of t equals that, how does it show that any solution can be represented as the sum?
Okay. So any solution can be represented in this form, right? So do you agree with this? So x of t is this linear combination. Why? Because x of t is an n vector. with n components, right? And vk form the basis. So for any value of t, x of t is this linear combination. And the second step is to show that these coefficients are of this form. And this will prove that any solution can be represented in this form. So we took any solution, then any solution has this form, and after this I proved that these coefficients are of this form. And this proves our theorem. Hope it is clear. Shall I go further? Well, so now let's discuss an example. I think it is important to see how it works. So example, maybe I will use this part of the blackboard. Let's solve this differential equation. X is a two-dimensional vector, so this differential equation means that we actually solve the following. Or maybe prime to the vector, or prime to each component. 1, 3, 1, negative 1, x1, x2. The first we discussed last seminar was to reduce this two-dimensional differential equation to a single second-order differential equation, right? But the second way is to find eigenvectors and eigenvalues and apply theorem number 1. Let's do this. Let's proceed in this way. And so the first step is to find eigenvectors and eigenvalues. The first step is to find eigenvalues. To find eigenvalues, we should find the matrix A minus lambda I and find the determinant of this matrix. It is 1 minus lambda, 3, 1, minus 1 minus lambda. The determinant of this matrix is equal to lambda minus 1 times lambda plus 1 minus 3. It is equal to lambda squared minus 1 minus 3, lambda squared minus 4. It is lambda minus 2, lambda plus 2. This is a characteristic equation. And we can see that there are two eigenvalues, lambda 1, which is equal to 2, and lambda 2, which is negative 2. Next, let's consider the first eigenvalue, lambda 1 equals 2, and now our goal is to find the eigenvector, an eigenvector. To do this, we should substitute 2 for lambda in this matrix, and we will get negative 1, 3, 1, negative 3. Okay, is it clear now? So how to obtain this matrix? This was studied last year, but maybe it is important to recall some steps. So we should substitute 2 for lambda in this matrix. And then to find a vector x1, x2 such that this product is trivial. So solve this linear equation. It is the same as minus x1 plus 3x2 equals 0. And I don't want to find all the solutions of this equation, but so it is enough to find some just one non-trivial solution. And so the vector v1, 3, 1 satisfies this equation. This is an eigenvector associated to the eigenvalue of 2. Sorry?
How did you get the 3 and 1?
So multiply. So we are looking for the vector x1, x2 such that this product is a trivial vector, right? So I multiply the rows of the matrix by this column, and so if I multiply -1 by x1, I will get minus x1, and then plus 3x2, and I'm trying to find the solution of this equation. The second equation will be the same. It will be x1 minus 3x2, the same. Right.
And you find x1 and x3 and
okay.
Okay.
Right. So I need another eigenvector. Lambda 2 equals -2. I should substitute -2 for lambda in this matrix, and I will get 3, 3, 1, 1. And I think it is not difficult to guess the solution. What is the solution of this? So 1 minus 1, for example. V2 will be 1 minus 1. Okay. So we get two vectors. Are they linearly independent or not? They are linearly independent because they are not collinear, right? They are not proportional, so they are linearly independent. But generally, the theorem was proved last year. It was proved in the course of linear algebra that if the matrix has n distinct eigenvalues, then the corresponding eigenvectors form the basis. They are linearly independent. So in particular, these two vectors are linearly independent. And so the step number 3, so it was step number 2, I think. And step number 3, to write down the solution of this differential equation. The solution will be, so x of t is equal to the linear combination of these vectors with coefficients e to the power 2t times the first vector plus e to -2t times 1, -1. So this is a solution. This is the answer. So this can be written in terms of coordinates. And plus constants. I have forgotten arbitrary constants. Well, so just a moment. C2 times e to the power -2t times 1, -1. Okay. And now if we want to rewrite this solution in terms of coordinates, it will be, so the function x1 of t will be equal to, or maybe, so I will write the answer in the form x of t equals 3c1 e to the power 2t plus c1 e to the power c2 e to the power -2t, and the second coordinate will be c1 e to 2t minus C2 e to the power minus 2t. So this is the answer. In terms of coordinates, in terms of components. Huh?
Can we remove 3?
Remove 3. So C1 is the same in both components. So if we remove 3, then we should divide C1 by 3. So we can replace we can replace 3C1 by some new constant. Then we need to divide this constant by 3.
And if the matrix has complex eigenvectors.
Right, complex eigenvectors. Now we will discuss this situation if the matrix is complex. So this is now it's time to discuss complex eigenvectors and eigenvalues. It is very important, of course, and very important part of our study. What shall we do then? So first, I will state and prove a very important lemma, and after this, we will consider an example with complex eigenvectors and eigenvalues. So, lemma 2. If A is a real matrix, so if A, is a real matrix with a non-real means complex, non-real eigenvector, eigenvalue lambda, and associated eigenvector V, then so first I state that A has an eigenvalue lambda bar complex conjugate, right? This is the complex conjugate. If lambda is non-real and if lambda is an eigenvalue of A, then lambda conjugate is also an eigenvector, an eigenvalue. And eigenvector V conjugate. So this is not this bar is not the notation of the vector, but this shows that this is the complex conjugate to V, complex conjugation. Right, and part number 2, we can replace so the vectors the linear combination of vectors of the vectors e to the power lambda t v and e to the power lambda bar t v bar, it's a complex conjugate, can be replaced. So in the general solution, I need this formula. I think I will give the number to this formula. Let it be formula number 1. So this is the form of a general solution of a linear homogeneous equation. So the second statement states that we can replace linear combination of these two vectors by of these two vectors, so in one by, so can be replaced by the linear combination of real part of e to the power lambda tv and the imaginary part of the same vector. And this will be real. Okay. So the problem is we have, so suppose we have the complex eigenvalue lambda, so non-real lambda. Then we have a complex vector, so a vector v with complex coordinates. So a linear combination will give us a solution to the differential equation, but we want real solutions. So we should replace complex numbers, but some real parts maybe of these vectors. And our Lambda states that we can replace complex components with real components. So imagine a real part of this vector and imaginary part of this vector will be real, and so and the linear combination of these two vectors can be replaced by a linear combination of these two vectors. And now we will, I'd like to prove this. So the first statement, statement number 1, let's show that lambda conjugate and v conjugate are also solutions. Okay, so since we know that AV equals lambda v, it is given because lambda is an eigenvalue and v is an eigenvector, so this is given. Then let's consider a v conjugate. How can we find this? So A is a real matrix. So this means that A conjugate equals A, because it is real. So it is equal to A conjugate v conjugate, this product. It is equal to, by the rule of the multiplication of complex numbers, that this product is equal to AV conjugate. Then we know that AV equals lambda v conjugate, and this is equal to the product lambda conjugate times v conjugate. So we have proved that v conjugate is an eigenvector associated with the eigenvalue lambda conjugate, right? So the first part is proved. Next, let's prove the second part. From the second part, let's try to find the real part of the vector e to the lambda tv. How can we represent the real part of the complex number? So I will use this part of the blackboard. Okay, so I'd like to discuss, to recall something. Okay, so if z is a complex number having the form a plus bi, how can we find the real part of z. Z bar, so conjugate is equal to a minus bi. Okay. Is it possible to find real part of z through the, in terms of linear combination of z and z conjugate? Is it possible to find the formula for real part of z? We should add them together, right? Z plus z bar conjugate divided by 2. Well, correct. What about in z? I think subtract z minus z bar, and we will get 2bi, and so we need to divide by 2i. Well, so let's use this fact. So the real value of the vector, so what does it mean? So the vector has several components, but for each component of this vector, it is true that the real part is equal to e to the power lambda t v plus e to the power lambda bar lambda conjugate v conjugate divided by 2, and e to the power lambda t v is equal to e to the power lambda t v minus e to the power lambda bar lambda conjugate t v conjugate divided by 2i. Let's discuss these two vectors. So this is a vector, and this is also a vector. Is it true that these two vectors so is it true that this is a solution of our differential equation? Is this a solution of our differential equation? So equation is here, this equation. Yes, because this is a linear combination, right? Right, but our constant is 1/2 and 1/2. So if we take ck's to be equal to 1/2 and 1/2, then we will get the linear combination of two vectors, and so it is a solution. So the real part of this vector is a solution. The imaginary part of this vector is also a solution with coefficients 1 divided by 2i and minus 1 divided by 2i, with these two coefficients, right? And so these two vectors are solutions. On the other hand, from these two equations, we can represent this vector as the linear combination of these two vectors, right? So we can see that these are solutions, and we can see that span and e to the lambda tv equals span The span means the set of all linear combinations of these vectors, right? The span of e to the power lambda tv and e to the power lambda conjugate tv conjugate. And so this means that this part, the linear combination of these two vectors, can be replaced by the linear combinations of these two vectors. So this completes the proof. Theorem is proved. And now let's discuss an example of this. Let's try to solve something with complex eigenvectors and eigenvalues. So this was example number 1. And example number 2 now. Example number 2, x prime equals, let's try to solve this. Well, so our matrix, so first let's find eigenvalues. The characteristic equation is a minus lambda I, the determinant of this is equal to, so the determinant of negative lambda, negative 1, 1, negative lambda, lambda squared plus 1, lambda 1 is I, and lambda 2 is negative I. They are complex conjugate. It was proved last year in the course of linear algebra. So if we have a polynomial with real coefficients, then the complex roots appear in pairs. So a root and its complex conjugate is also a root, right? So it is enough to consider just one eigenvalue. So for this eigenvalue, we have the following matrix. Substitute I for lambda, and we will get this. Then we need to solve this linear equation, from which we have minus, so minus x1 minus I x1 minus x2 equals 0. So it is the same as x2 equals minus I x1. So if we need just one vector, not many vectors. So if x1 equals 1, for example, then x2 equals negative I, and we have an eigenvector v1 of the form 1, negative I. Well, next, according to this rule, we need to find the real part of this vector and the imaginary part. So first, let's find e raised to the power. So we need to find, it's step number 2. Let's find e to the power it times v times the vector 1, negative I. So first we will find this, and next we will take the real and the imaginary part of this vector according to this rule, right? So this vector, next we will take real part and imaginary part. E to the power it, what is it? Euler formula, cos t plus I sine t. 1 negative I equals to cos t plus I sine t and minus I cos t plus sine t. And next, we should split this vector into real part and imaginary part. It is equal to cos t sine t plus I multiplied by sine t minus cos t. Is it clear? Next, we should, the answer to this differential equation will be the linear combination of these two vectors. Next, we should take linear combination of this vector and this vector. So the answer will be is a linear combination of these vectors. So C1 cos t sine t plus C2 sine t minus cos t. So we're done. Now we will discuss exponential of a matrix, because sometimes, so first of all, I will show you an example number 3. Okay, let's consider differential equation of the form 0, 1, 0, 0 times x. Okay, can we solve this differential equation using the method of eigenvectors and eigenvalues? Well, let's try to find eigenvalues. Right, so minus lambda, the characteristic equation first. Lambda squared equals 0. So this is the multiple root. Lambda 0 equals 0 is a root of a characteristic equation. There are no roots, no other roots. And then let's try to find eigenvectors. Let's substitute 0 for lambda in our matrix. We will get this. We're looking for the vector x1, x2 such that this product is a 0 vector, is trivial. Then this means that x2 equals 0, and an eigenvector will be so 1 and 0, not I, so 1 and 0.
Oh, yeah.
So only one eigenvector and one eigenvalue and one eigenvector. So we can't find the basis of eigenvectors. Right? In this situation, it is impossible to find the basis of eigenvectors because we have a Jordan cell, but we will discuss Jordan cells next time, I think. But this is the problem. So if we have a basis consisting of eigenvectors, then we are done. We can write a formula for the general solution of a differential equation, and we are done. But sometimes we can't find the basis consisting of eigenvectors. Okay, so now to discuss how to treat this situation, how to handle this situation. So I'd like to introduce a new notion. It is called the exponential of a matrix. Or a matrix exponential. This means that I'd like to introduce this operation, e raised to the matrix power. How to raise e to some power a, matrix power. What shall we do to find this? There is a formula. So we should take an identity matrix, then add I, so and a plus a squared half, so multiplied by the coefficient 1/2. So I may rewrite it in the form 1/2 times a squared plus 1 over 3 factorial a cubed plus ... So this is the it can be in the compact form, it can be rewritten in the form 1 over k factorial a to the power k. K runs from 0 to infinity. Okay. So to find an exponential of the matrix, we can use this formula. Well, we can try to apply this formula if you want. For example, then let's consider some examples. Right? Example number 4, for example. Right? Example number 4. Let A be equal to, let it be a diagonal matrix. For example, 2, 3. And let's try to apply this formula. What is A squared?
Just A multiplied by A.
Right, A multiplied by A. Mm-hmm. 4, 0, 0, 9. So since A is a diagonal matrix, then A to the power k will be 2 to the power k, 0, 0, 3 to k. This is true only for diagonal matrices, not for any matrix, because we need to multiply two matrices. Well, then what is e to a? Identity matrix first, 1, 0, 0, 1, plus a, which is 2, 0, 0, 3, plus 1 half, 2 squared, 0, 0, 3 squared, 1 over k factorial, 2 to the power k, 0, 0, 3 to the power k, plus dot, dot, dot. What is the result? So it will be here, 1 plus 2 plus 1 half times 2 squared, plus 1, 6 times 2 cubed, plus dot, 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 plus 1 over k factorial, 2 to the power k, 0, 0, and the same for 3. Okay, so I will show how to. So we will discuss the procedure of finding e to a next time, but now let's write the resulting matrix. What is the result? What is this? What is this? Can we rewrite it in some other form? What does it mean?
Okay, I don't know.
Who knows? Follow? Who knows? What is it?
We could just say let this equal to x and let this equal to y.
X and yes, but can you obtain this? Can you find x and y?
Probably there's a way.
So okay, do you remember anything about Taylor formulas? Taylor formula. What is it? Taylor formula. What is it? What is e to x? Do you know that Taylor expansion of this function about this x equals 0, about the origin? 1 plus x squared half plus x cubed 3 factorial plus dot 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 plus x to k factorial plus dot dot dot, right? Right. So you can see that this is, we can use this formula to find this infinite sum. What is the first entry? So e squared, right? 0, 0, e cubed. Correct. So e raised to the power of this matrix is just e squared 0, 0 cubed. So for a diagonal matrix, this is true, so it can be proved in the same way that if we raised e to a diagonal matrix, we will get this answer. So very easy. But now, so today I want to discuss some theory of general theory of exponential of a matrix. And first of all, we should discuss the problem. So we should discuss. We should prove that this is well defined and exists for any matrix of A. So any matrix A. For any A, we can find the exponential of the matrix. Okay. So to do this, I'd like to recall some facts from theory of linear operators, from calculus and linear algebra. And in what follows, we will need the notion of a normed vector space. Normed vector space. It comes from calculus. X. So X is a vector space. How can we introduce the norm? What is it? What is the norm? The norm. What is the norm?
What is the norm?
Normed vector space. How can we define the norm? Is a function not necessarily the square root of sum of squares, right? It is this norm is the standard norm in Rn, but sometimes we want to introduce the norm in the infinite dimensional space. Okay, so this is the function from x to r plus. So this is a non-negative function, right? It takes non-negative values. Okay, and then there are three properties which should be satisfied. So the first property is triangle inequality property number 3. The norm of x plus y is less than or equal to the sum of norms. Okay, so for any in x and the y in x, right? What about first? Right, scaling property, right? The norm of lambda x is equal to the absolute value of lambda times the norm of x, where lambda is some scalar, right? Scalar for any x in x and the scalar lambda, and okay, positivity, right? The norm equals 0 if and only if x is a 0 vector. This is the normed vector space. Well, if we have a normed vector space, then we can introduce the notion of a distance. But now we need to introduce. So we need the definition of the operator norm. Operator norm. Do you know what is it? Operator norm. So we can see the vector space of all linear operators in Rn. The set of all linear operators in Rn, linear functions, linear, right? linear operators in Rn. Okay, so a linear operator so means that f of x plus y, lambda x plus mu y equals lambda f of x plus mu f of y. So f is from Rn to Rn. If we fix a basis in Rn, then we can associate a matrix with any linear operator. We can associate a matrix, n by n matrix. Okay. So we can consider the set of all linear operators in Rn, and we can introduce the norm. So the norm of A by the formula, the following formula. It will be the supremum of Ax, the norm of Ax divided by the norm of x, where x is in R and z minus 0. Where so the supremum over all non-zero vectors in Rn. So this is the definition of the operator norm. Well, okay, so how can we prove that this is a finite number? So have you discussed this in calculus or not? No? Supremum, right, supremum, you know. I hope that supremum, you know. So the operator norm.
No.
Okay, well, so if we consider maybe, so let's discuss this definition. So if we consider all the vectors of norm 1, so all the vectors of with no, such that the norm of x is 1. So this is a sphere in Rn. It is a compact set. Compact set. Okay, and so what about the norm of Ax? This is a continuous function on the sphere. Is a continuous function on the sphere, and so since this the continuous function on a compact set is bounded and takes on its maximum and minimum value, right? Right. But if the norm of x is not 1, if for some y such that y is not 0 and the norm of y is not 1, we can represent y as lambda times x, where the norm of x is 1. And if we consider ay divided by y, we get the following: the norm of a times lambda x By scaling property, it is the norm of lambda times norm of ax divided by the norm of lambda times norm of x. We can cancel out lambda, and we will get this. So it is sufficient to consider not all. So we need not consider all non-zero vectors, but instead we can consider all the vectors from this sphere, right? In this definition. So I have introduced the operator norm, and now I think we will have a break. So we will continue to discuss this theory next time.